The last normal day. There is a star in the sky right now that does not know it is about to die. This is not a poetic statement. Stars do not know anything. But the phrasing captures something real. The process that will end this star has already begun, deep inside it, in a region so far from the surface that the surface has no information about it yet. The light leaving the star's surface right now was generated in the core hundreds of thousands of years ago. The star's exterior is showing you its past. Its interior is already living in its future. And the future for this particular star is not good. You're lying somewhere. The body has been horizontal long enough that the idea of being vertical again feels like a project. Outside or above you, or in some direction that the architecture of your building is not currently letting you access, there is a sky. And in that sky there are stars. And some of those stars, a specific, calculable, non-trivial fraction of them, are in the process of dying right now, at this moment, while you are here, while the building is quiet, while the night is doing what nights do. The question this video is about is simple to state and almost impossible to fully answer. What actually happens? Not the summary, not the textbook version with the diagram and the labelled phases. What actually, physically, mechanically happens inside a star when it runs out of the thing that has been keeping it alive? The thing that has been keeping it alive is pressure. Not the kind of pressure you feel when something heavy is placed on your chest, though that is the right family of sensation. The pressure inside a star is the outward push generated by nuclear fusion, the process by which hydrogen nuclei, under conditions of temperature and density that do not exist anywhere else in the solar system, are forced close enough together to fuse into helium, releasing energy in the process. That energy, moving outward through the star, creates a pressure that pushes against the inward pull of gravity. The star is, at every moment of its stable life, a negotiation between these two forces. Gravity trying to collapse everything inward, fusion pressure pushing everything outward, and the two forces matched against each other produce a stable object that can sit in space for millions or billions of years without resolving the argument. When the fuel runs out, the argument resolves. Gravity wins. But the way it wins, the specific sequence of events, the physics of the collapse, the violence and the strangeness and the things that happen in the fraction of a second after the core gives way, is not something most people have ever actually sat with. The summary is, the star explodes, and the summary is accurate as far as it goes, which is not very far. What actually happens in that explosion? What comes out of it? What is left behind? And why any of it is possible at all? These are things that take longer to explain and that are, once explained, considerably stranger than the summary suggested. So this is the longer version. Start with what a star actually is, structurally, because the structure matters for what happens when it ends. A main sequence star, a star in the stable hydrogen-burning phase that the Sun is currently in, is not a uniform ball of hot gas. It has layers. The core is where the fusion happens, where temperatures reach tens of millions of degrees, and the density is high enough to force hydrogen nuclei into contact. Around the core is a radiative zone, where energy produced in the core slowly diffuses outward through radiation, a process so slow that a photon generated in the core can take 100,000 years to reach the surface through repeated absorption and re-emission. Around the radiative zone is a convective zone, where hot plasma rises and cooler plasma sinks in circulation patterns, carrying energy outward more efficiently than radiation alone. and at the surface is the photosphere, the visible layer, the one whose light travels 8 minutes to reach Earth and then arrives at your eye or your camera or your telescope. The star is a machine, a layered, self-regulating, gravity-powered fusion machine that has been running on the same basic principle since it formed from a collapsing cloud of gas. And like all machines, it has a fuel supply, and the fuel supply is finite. How long does the fuel last? It depends on the mass of the star, and the relationship is counterintuitive. You might expect that a more massive star having more fuel would last longer, but a more massive star also has more gravity pressing inward, which means the core has to generate more pressure to maintain the balance, which means it has to fuse hydrogen faster, which means it burns through its fuel supply at a rate that more than offsets the larger initial stockpile. The Sun, a fairly average star by mass, will spend about 10 billion years on the main sequence. A star 10 times the mass of the Sun will spend only about 20 million years, 1,000 times shorter, despite having vastly more hydrogen to burn. The most massive stars, the ones 50 or 100 times the mass of the Sun, burn so intensely that they exhaust their fuel in just a few million years. They live brilliantly and briefly, which is why the universe, at 13 billion years old, still contains many low-mass stars from its early history, but very few of its original high-mass stars. Those have all been dead for billions of years. The mass of the star determines not just how long it lives, but how it dies. And the deaths are different enough from each other that they almost feel like they belong to different categories of event. A star like the Sun dies quietly, by cosmic standards. A star much more massive than the Sun dies in one of the most energetic events in the observable universe. Both processes begin the same way. The core runs out of hydrogen, but from that shared starting point, the paths diverge sharply and lead to very different ends. This video follows the more violent path, the high mass star, the one whose death is not quiet. Not because quiet deaths are unimportant, they are not, and there is extraordinary physics in the death of a sun-like star, which produces the white dwarfs and planetary nebulae that are among the most beautiful objects astronomers observe. But the high-mass stellar death is the one that contains a core collapse, a shock wave, a supernova, the formation of a neutron star or a black hole in a fraction of a second, elements heavier than iron being forged in the explosion and scattered into space to eventually become planets and oceans, and in some non-trivial fraction of cases the atoms in living organisms. Your iron is supernova iron. The calcium in your bones was made in a stellar explosion. The oxygen you are breathing right now was forged in the core of a star that died billions of years ago, and whose remnant, if it still exists, is somewhere in the galaxy, cooling slowly, almost certainly unobserved. This is the story of how that happened. This is what happens when a star dies. The hydrogen problem. Inside the core of a massive star, 4 hydrogen nuclei are becoming 1 helium nucleus. This is happening billions of times per second, across a volume of space roughly the size of a small planet, at a temperature of around 15 to 40 million degrees Celsius, under pressures that would crush any material object into something unrecognizable. It is happening right now, in stars across the galaxy, as it has been happening since the first stars formed a few 100 million years after the Big Bang. It is the most common nuclear reaction in the observable universe, and it is the reason stars exist as stable objects rather than as collapsing clouds of gas or expanding balls of plasma. The process is called the proton-proton chain in lower mass stars. In higher mass stars, the ones this video is following, it is dominated by the CNO cycle, in which carbon, nitrogen, and oxygen act as catalysts, facilitating the fusion of hydrogen into helium without being consumed in the process. The details of the cycle are layered and precise, involving a sequence of nuclear reactions that cycle through several isotopes before returning to the starting catalyst. But the net result is the same. Hydrogen goes in, helium comes out, and energy is released. The energy released per fusion event is small, extraordinarily small. A single proton-proton fusion event releases about 26 million electron volts of energy, which sounds like a lot until you convert it to more familiar units, and find it is roughly 4 trillionths of a joule, less than the kinetic energy of a flying mosquito. The Sun is luminous because it is performing this reaction roughly 9 times 10 to the 37th power times per second. The number has 38 digits. It is not a number that intuition can hold. For millions of years this works. The hydrogen fuses into helium, the energy maintains the pressure maintains the balance, and the star sits in space doing exactly what a star is supposed to do, shining, maintaining its size, converting its fuel into light and heat, and the outward radiation pressure that prevents gravity from winning. But the helium accumulates. This is the problem. Not that helium is toxic to the fusion process exactly, but that helium does not fuse under the same conditions that fuse hydrogen. Helium requires higher temperatures and higher pressures to begin its own fusion reactions. And while the star is in its main sequence phase, the conditions in the core are calibrated for hydrogen fusion, not quite extreme enough to ignite helium. So the helium produced by hydrogen fusion just sits there, in the core, accumulating, not participating in any reactions, not generating any pressure. What helium does do, being inert under these conditions, is respond to gravity. It settles, it compresses. The helium core grows denser and hotter as more hydrogen is fused in the shell around it, because as the core contracts, gravity does work on it, converting gravitational potential energy into heat. The core gets hotter even as it is failing to fuse. Here is the specific sequence, and it matters because each step sets up the next and the one after that, all the way to the end. First, the hydrogen in the core is exhausted. Fusion in the core stops. Gravity begins to win locally in the core. The core contracts. Second, as the core contracts, it heats up. The hydrogen in the shell surrounding the now inert helium core is still present, and the increasing temperature from the contracting core ignites hydrogen fusion in that shell. The star now has a burning shell rather than a burning core. The energy output from the shell is actually greater than the energy output from the core had been, because the shell is hotter. Third, the increased energy output pushes the outer layers of the star outward. The star expands dramatically. The outer layers cool as they expand, shifting the star's color toward red. The star has become a red supergiant, a star whose radius may be hundreds of times its original size, large enough to engulf the inner planets of a solar system if placed at the Sun's position. Betelgeuse, the bright reddish star in the shoulder of Orion, is a red supergiant. It has expanded to somewhere between 700 and 1,400 times the radius of the Sun. The uncertainty is real. Measuring the size of a star is harder than it sounds. If you placed Betelgeuse where the Sun is, it would extend past the orbit of Jupiter. It is in this late phase of its life, doing exactly what this chapter describes. Fourth, the core continues to contract and heat. Eventually, at temperatures around 100 million degrees, the helium in the core reaches the ignition point for helium fusion. Helium nuclei begin fusing into carbon and oxygen. A new energy source is ignited. The core stabilizes temporarily against the pressure of helium fusion, but helium is a less efficient fuel than hydrogen. The helium burning phase lasts a fraction of the time the hydrogen burning phase lasted. For a massive star that spent 20 million years burning hydrogen, the helium burning phase may last only 1 million years or so. The fuel is burning faster because the conditions are more extreme and the energy per fusion event is less favorable. Fifth, the helium in the core is exhausted. Again, the burning moves to a shell. The carbon-oxygen core left behind by helium fusion is now inert, contracting, heating. Carbon ignition begins at around 500 million degrees. Carbon fuses into neon, sodium, magnesium. The carbon burning phase lasts perhaps 1,000 years, then neon burning, then oxygen burning, then silicon burning, each phase shorter than the last, each requiring a higher temperature and producing a less favourable energy yield, each phase building up an ash of heavier elements in the core that will itself eventually ignite, or fail to. The star is now an onion, a layered structure of burning shells, each burning a different fuel at a different temperature, nested around a core that is always the inert ash of the most recently completed burning phase. At the end of this sequence, the core is iron, and iron is where the sequence stops. Not because the conditions are not extreme enough to fuse iron, they are, but because iron fusion does not release energy. Iron is the most stable nucleus in the periodic table, the nucleus with the highest binding energy per nucleon, the endpoint of nuclear stability. Fusing iron requires energy rather than releasing it. The star cannot use iron as fuel. The iron core is not a new fuel source, it is a dead end. The iron core grows. Silicon fusion in the shell above it continues to add more iron. The core is not generating any pressure from fusion reactions. It is being held up against gravity entirely by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being compressed into the same quantum state, which provides a pressure that does not depend on temperature, and that can, up to a point, support the core against collapse. Up to a point, the iron core grows. It has to stay below a critical mass to be supported by electron degeneracy pressure. That mass is called the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. As silicon fusion in the shell continues to add iron to the core approaches this limit. When it reaches it, when the iron core exceeds approximately 1.4 solar masses and electron degeneracy pressure can no longer hold it, the core collapses. What happens next occurs in less than a second, and it is, by a significant margin, the most violent event that can happen to a single star. The collapse. The core is at the limit, not approaching it, at it. The iron mass has reached the point where electron degeneracy pressure, the quantum mechanical resistance that has been holding the core against gravity for the duration of silicon burning, is no longer sufficient. Gravity has been patient. It has been pressing inward for millions of years, held at bay by one burning phase after another, each one buying time, each one building more iron, each one bringing the core closer to this moment. The moment arrives without announcement. There is no warning signal, no precursor detectable from the outside. The surface of the star, hundreds of millions of kilometers away from the core, is still doing what it has been doing. Glowing, convecting, shedding stellar wind into space. The surface does not know. The information about what is happening in the core travels at the speed of light through the star's interior, and the star's interior is large enough that even light takes seconds to traverse it. The core collapses before the surface knows it is happening. The collapse is fast. Not fast in the way a building demolition is fast, or fast in the way a car crash is fast. Fast in a way that requires the word fast to carry more weight than it usually does. The iron core, which before the collapse was roughly the size of Earth, tens of thousands of kilometers across, collapses to a sphere roughly 20 kilometers across in less than a second, in approximately a quarter of a second. Let that settle for a moment. An object the size of Earth, compressed to an object the size of a city, in a quarter of a second. The collapse velocity at the inner edge of the core reaches approximately 70,000 kilometers per second, about a quarter of the speed of light. This is not a metaphor. This is the actual infall velocity, derived from the equations of stellar structure under conditions where both general relativity and nuclear physics are relevant simultaneously. The collapse is relativistic. It is fast enough that the language of everyday experience does not apply. What stops it, what could possibly stop it, is the nuclear force. As the core collapses and the density increases past the density of an atomic nucleus, the strong nuclear force, which is repulsive at very short ranges, begins to resist further compression. The protons and electrons in the core, under the extreme pressure of collapse, have undergone a process called inverse beta decay. The electrons have been forced into the protons, combining to form neutrons and releasing neutrinos. The core, in the space of that quarter second, has become almost entirely neutrons, and neutrons, like electrons before them, have a quantum degeneracy pressure. Neutron degeneracy pressure, the resistance of neutrons to being compressed into the same quantum state. And unlike electron degeneracy pressure, neutron degeneracy pressure, augmented by the repulsive component of the strong nuclear force, is sufficient to halt the collapse. The core bounces, not a gentle rebound, not a slow expansion. The core, which has overshot the equilibrium density of nuclear matter in the violence of its collapse, snaps back. The inner core rebounds outward. The infalling outer layers of the core, which have not yet reached the bounce point, are still moving inward at a quarter of the speed of light. They collide with the rebounding inner core. The collision generates a shock wave. This shock wave is, in principle, the thing that will blow the star apart. It is the origin of the supernova. It begins at the core and moves outward through the star, carrying an enormous amount of energy, on the order of 10 to the 44 joules, which is roughly the total energy the Sun will radiate over its entire 10 billion year lifetime, released in a few seconds, in principle. In practice, the shock wave almost immediately runs into a problem. As it moves outward through the iron core, through the iron that has not yet fallen into the bounce point, the shock loses energy. It loses energy because it is photo-dissociating iron nuclei, breaking them back apart into protons and neutrons, which requires energy input rather than releasing it. Each iron nucleus the shock wave breaks apart costs the shock approximately 8.8 mega-electron-volts of energy. The shock is destroying the nuclear structure it encounters, and the energy cost is substantial. The shock wave stalls. Typically within about 100 to 200 milliseconds after the bounce, the shock has lost enough energy to stop propagating outward. It sits at a radius of roughly 100 to 200 kilometers from the core, still present, still hot, but no longer moving outward. And if the shock stays stalled, the star does not explode. The outer layers continue to fall inward. The neutron star is buried. What follows is not a supernova, but a failed supernova, a star that simply collapses into a black hole without the dramatic explosion. This happens. It is not the only outcome, but it happens. What saves the shock wave, in the cases where the star does explode, is neutrinos. And here the physics becomes something that resists normal language, because what neutrinos normally do is nothing. They are the most antisocial particles in the Standard Model. They interact with matter only through the weak nuclear force and gravity, both of which are negligible at ordinary densities. A neutrino can pass through a light year of solid lead with only a 50% chance of interacting. They pass through the Earth by the trillions every second. They pass through you, right now, without interacting. But the newly formed neutron star is not ordinary density. It is nuclear density, the densest stable configuration of matter that exists in the universe. At nuclear density, even neutrinos interact. The neutron star is briefly opaque to neutrinos. The core collapse has released an enormous number of neutrinos, primarily through the inverse beta decay reactions and through pair production processes at the extreme temperatures of the core. The energy carried by these neutrinos is staggering. Approximately 99% of the total energy of the collapse, about 3 times 10 to the 46 joules, is emitted as neutrinos. The visible explosion, with all its light and shock energy, is only about 1% of the total energy budget of a core collapse supernova. The neutrinos dwarf everything else. As these neutrinos stream outward from the core, a small fraction of them, perhaps a few percent, are absorbed by the matter in the stalled shockwave region. A few percent of an enormous number is still a large number. The energy deposited by this neutrino absorption reheats the material behind the shock, reviving it, giving it the energy it needs to resume its outward propagation. This is called the neutrino-driven mechanism. It is the leading explanation for how core collapse supernova work, and it is the result of decades of theoretical development, increasingly sophisticated computer simulations, and the one direct observational confirmation we have, the neutrinos detected from supernova 1987A. On February 23, 1987, a star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years away, exploded. The neutrinos arrived at Earth approximately 3 hours before the visible light, because they were produced in the core collapse while the shock wave was still travelling through the star, and because neutrinos move at very close to the speed of light and pass through the star's matter almost without interaction, while the light had to wait for the shock wave to reach the surface. The neutrino detectors at Kamiokande in Japan, IMB in Ohio, and Baksan in Russia recorded a total of 25 neutrino events within a 13-second window. 25 individual detections out of the incomprehensible flood of neutrinos that passed through Earth that day. The vast majority passed through undetected, as neutrinos do. Those 25 detections confirm the basic picture of core collapse and neutrino emission. They remain the only direct detection of neutrinos from a supernova in the modern era of neutrino astronomy. Back to the shock wave. It is moving now. Revived by neutrino energy, it is propagating outward through the star at a significant fraction of the speed of light. It has thousands of kilometers to travel before it reaches the surface, and the journey takes several hours. During those hours, the surface of the star still does not know what has happened. The information is travelling upward through the star, but the star is large, and even at the shockwave speed, the surface is far away. When the shockwave reaches the surface, when it breaks through the photosphere and into the surrounding space, the star's exterior brightens suddenly and enormously. This is the shock breakout, a brief, intense pulse of X-ray and ultraviolet radiation that lasts only seconds to minutes, depending on the size of the star. It is the first visible signal of the supernova, and it is the one that most telescopes are not positioned to catch, because nobody knows exactly which star in the sky is about to explode, and the breakout signal is over before any observatory can be pointed at it. What follows the breakout is the sustained optical brightening of the supernova, the light curve that rises over days to weeks, and then slowly fades. This is what astronomers generally mean when they say they observed a supernova. The optical brightening of the ejector, the material blown off by the shock wave, which continues to radiate as it expands into space. The light from a supernova at its peak can outshine an entire galaxy of hundreds of billions of stars, briefly, for a few weeks, and then it fades, over months to years, as the expanding cloud of debris becomes more diffuse and cooler. The star, in the course of this event, has blown off most of its mass. The outer layers, the hydrogen envelope, the helium shell, the intermediate layers of carbon, oxygen, neon, are all moving outward now at thousands of kilometers per second, carrying with them the elements that were synthesized in those layers over millions of years of burning. And within the explosion itself, in the extreme temperatures and neutron-rich environment of the expanding shockwave, additional nucleosynthesis occurs. Elements heavier than iron, elements that cannot be made by stellar burning, are forged in the violence of the explosion and carried outward with the ejector. Gold, platinum, uranium. These are supernova elements. They exist in the universe because stars died explosively, but the ejector is only part of what is left. The other part is what the core became in the first quarter-second of the collapse. What is left? The explosion has happened. The shockwave has passed through the star, torn the outer layers loose and sent them outward at thousands of kilometers per second. The star, which an hour ago was a red supergiant hundreds of times the size of the Sun, is now, from the outside, a rapidly expanding cloud of hot gas, brightening, cooling, spreading into the surrounding interstellar medium. In a few thousand years, this cloud will become a supernova remnant, a beautiful, structured nebula, visible from Earth with a telescope, a record of the violence that produced it, the Crab Nebula. Cassiopeia A, the Veil Nebula. These are the records of stars that died. The Crab Nebula, 6,500 light-years away, is the remnant of a supernova observed by Chinese astronomers in 1054 CE. A star that appeared in the daytime sky for 23 days, bright enough to see in full sunlight. What you see today when you look at the crab through a telescope is the ejector from that explosion, still expanding, still structured, still carrying the imprint of the shockwave that created it. At the center of the Crab Nebula is a pulsar, a rapidly rotating neutron star spinning 30 times per second, sweeping beams of radiation across space like a lighthouse. This is what the core of the star became. The neutron star is one of the strangest objects in the universe. It is the remnant of the iron core that collapsed. In the quarter-second of that collapse, the core went from Earth-sized to city-sized, from iron-rich to neutron-rich, from a thermally supported stellar core to something for which normal matter has no analogy. The neutron star is typically about 20 kilometers in diameter and about 1.4 times the mass of the Sun. It is the most dense, stable configuration of matter known to exist. The density of a neutron star is approximately 10 to the 17th kilograms per cubic meter. For comparison, the density of water is 1,000 kilograms per cubic meter. The density of lead is about 11,000 kilograms per cubic meter. The density of an atomic nucleus, which for a long time was considered the ultimate density of matter, is approximately 2.3 times 10 to the 17 kilograms per cubic meter. A neutron star has roughly nuclear density throughout its entire interior. It is, in a meaningful sense, a star-sized atomic nucleus. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth. This is the kind of number that tends to get cited and then immediately filed under things that are extreme but not imaginable. It is worth trying harder. 10 million tons in a teaspoon, the mass of a small mountain, in a volume of material smaller than your thumbnail. The neutron star forms hot, extraordinarily hot, on the order of 100 billion degrees in the immediate aftermath of the collapse. It cools rapidly, radiating neutrinos copiously for the first 10 seconds, then more slowly over thousands of years. By cosmic standards, even a relatively young neutron star is cooling, slowly but measurably. What the neutron star is doing, physically, is complicated and not fully understood. The interior is stratified, like the star that produced it, but in ways that are determined by nuclear physics at densities we cannot replicate in any laboratory on Earth. The outer crust is crystalline, a lattice of neutron-rich nuclei embedded in a sea of free electrons. Below the crust, as density increases, the nuclei dissolve into a fluid of free neutrons and protons and other particles. Deeper still, at the very core of the neutron star, the density may be high enough for exotic states of matter, quark matter, strange matter, hyperons, to exist. We do not know. The physics of matter at these densities is beyond direct experimental reach, and the equations of state, the descriptions of how this matter behaves, are still debated. What we can observe from the outside is the neutron star's rotation and its magnetic field. Neutron stars rotate. All stars rotate. The Sun completes one rotation in about 25 days at its equator. When a stellar core collapses from Earth-sized to city-sized, the conservation of angular momentum demands that the rotation rate increase dramatically. The same principle that makes a figure skater spin faster when they pull in their arms, applied to an object undergoing a compression factor of hundreds of thousands. The result is neutron stars that rotate extremely rapidly, sometimes hundreds of times per second. The fastest known neutron star rotates at 716 times per second. 716 rotations per second. The equator of this object, a sphere 20 kilometers across, with more than a solar mass of material, is moving at approximately 24% of the speed of light. Neutron stars also have magnetic fields, very strong magnetic fields. When the stellar core collapses, the magnetic field of the star is compressed, along with the matter, amplifying the field strength by a factor proportional to the square of the compression ratio. The result is magnetic fields billions to trillions of times stronger than Earth's, Some neutron stars, called magnetars, have magnetic fields so strong that they distort the quantum vacuum around them, produce starquakes in their crystalline crusts, and emit bursts of X-rays and gamma rays detectable across the galaxy. The magnetic field, combined with the rotation, produces the pulsar phenomenon. Charged particles are accelerated along the magnetic field lines and emit beams of radiation from the magnetic poles. If the magnetic poles are not aligned with the rotation axis, and they generally are not, these beams sweep around as the neutron star rotates like a lighthouse. If the Earth happens to be in the path of the beam, we detect a pulse of radiation once per rotation. Pulsars are among the most precise clocks in the universe. The rotation rates of millisecond pulsars, the fastest rotators, are stable to better than 1 part in 10 to the 15th per year. This is comparable to the best atomic clocks humans have built. Astronomers use pulsar timing to detect gravitational waves, to test general relativity, and to study the interstellar medium. The precision is not incidental. It is a consequence of the extreme physics of the object doing the rotating. But neutron stars are not the only possible remnant of a core collapse. The outcome depends on the mass of the collapsing core, and mass, as established earlier, is where everything diverges. If the iron core that collapses is massive enough, the neutron star that forms in the first fraction of a second may be too massive to be supported even by neutron degeneracy pressure and the nuclear force. In this case, the collapse continues past the neutron star stage. There is no second bounce. The matter continues to compress indefinitely, or rather, until it has formed a black hole. The transition from neutron star to black hole is, in some cases, almost instantaneous. The neutron star may exist for only milliseconds before its own gravity overwhelms the last resistance. In these cases, the supernova explosion may fail entirely. The collapsing material falls into the black hole rather than being blown outward, and the star simply vanishes. From the outside, a star that was present in one observation is absent in the next, with no intervening explosion. This is called a failed supernova, or a direct collapse black hole. There is at least one strong candidate in the observational record, a star in the galaxy, NGC 6946, that brightened briefly in 2009, then disappeared. No supernova, no remnant, just absence. The mass boundary between neutron star formation and black hole formation is not precisely known, because it depends on the physics of matter at nuclear densities, the equations of state mentioned earlier, which are still uncertain. A typical threshold is thought to be around 2 to 3 solar masses for the remnant core. Stars whose iron cores produce remnants above this threshold will collapse to black holes. Stars whose cores produce lighter remnants will form neutron stars. The universe then produces 2 kinds of remnant from core collapse: neutron stars and black holes. Both are real, both are present in the galaxy, and both are consequences of the same basic process: a star running out of fuel and surrendering to gravity, played out under slightly different conditions. What the explosion leaves in the surrounding space, apart from the remnant at the centre, is the ejecta, the material blown off by the shock wave. And this ejecta is not uniform. It is chemically layered, carrying the composition of the different burning shells through which the shock wave passed. The outer layers, rich in hydrogen and helium. The inner layers, rich in carbon, oxygen, silicon. And throughout the ejecta, the heavier elements produced in the explosion itself, iron, nickel, cobalt, and the R process elements, gold, platinum, uranium, and everything else that requires a neutron-rich environment and extreme temperatures to assemble. The ejector expands. For thousands of years it expands, sweeping up the surrounding interstellar gas, slowing, cooling, becoming the structured nebula visible from Earth. Eventually it disperses into the interstellar medium, the gas between stars, enriching it with heavy elements. These heavy elements become part of the raw material for future star formation. New stars form from clouds of gas that include the ejector of dead stars. New planets form from the dust in those clouds. And on at least one of those planets, in at least one solar system, this enriched chemistry became the basis for biochemistry. The iron in your blood was made in a stellar core. The calcium in your bones was made in a helium-burning shell. The iodine in your thyroid, the gold in any jewelry you own, the uranium in the Earth's mantle, all of it forged in stellar interiors or supernova explosions and scattered into space by the deaths of stars that preceded the formation of the solar system. You're made of stellar remnants, not metaphorically, chemically, specifically, traceably, the quiet deaths. Not every star ends in an explosion. This needs to be said, and said clearly, before it gets lost in everything that followed the previous chapter. The supernova, the core collapse, the bounce, the shock wave, the neutron star or the black hole, is the death of a massive star, a star significantly more massive than the Sun. And massive stars, while spectacular, are not the most common type of star. Most stars in the galaxy are low-mass stars, stars with less than about 8 times the mass of the Sun. These stars outnumber the massive ones by a large margin, and they die differently. They die quietly. And the quiet death, it turns out, is not without its own strangeness. The Sun will not explode. It is worth saying this plainly because the cultural presence of supernovae is large enough that people sometimes absorb the impression that all stars explode eventually, or that the Sun's death will be similarly dramatic. It will not. The Sun will die in a way that is, by the standards of stellar astrophysics, relatively gentle, though gentle here means over a period of billions of years, while expanding to a size that would consume the inner planets and sterilize whatever remains of the outer solar system. Here is the sequence for a Sun-like star. The hydrogen in the core is exhausted. The core contracts, heats up, ignites hydrogen burning in a shell. The outer layers expand. The star becomes a red giant, smaller than the red supergiants produced by massive stars, but still large by comparison to its original size. The Sun, when it becomes a red giant in approximately 5 billion years, will expand to perhaps 200 times its current radius. Large enough to swallow Mercury and Venus, possibly large enough to swallow Earth, though this is uncertain and depends on mass loss rates during the giant phase. Eventually the helium in the core ignites. In a Sun-like star, this ignition is not gradual. It is sudden. The helium core of a low-mass star is electron degenerate, supported by electron degeneracy pressure, and degenerate matter has a peculiar property. It does not expand when heated the way normal gas does. This means that when helium fusion ignites in a degenerate core, the energy released heats the core but does not expand it to relieve the pressure, which means the fusion rate increases, which releases more energy, which heats the core more, which increases the fusion rate further, a runaway process called the helium flash. The helium flash releases in a few seconds energy comparable to the entire luminosity of the Milky Way galaxy. The entire galaxy, in seconds, from a single stellar core about the size of Earth, and yet it is not visible from outside the star. The energy is absorbed by the outer layers, and the star actually dims briefly. The helium flash, one of the most energetic events in the life of any star less than about 2 solar masses, is undetectable from Earth. After the flash, the core expands, the degeneracy is lifted, and helium burning proceeds in a more controlled way. The star settles onto the horizontal branch and burns helium for a while, not as long as it burned hydrogen, but not negligibly short either. Then the helium is gone. The core, now carbon and oxygen, is not hot enough to ignite carbon fusion. In a low-mass star, the temperatures required to fuse carbon, around 500 million degrees, are never reached. The carbon-oxygen core is inert. The star is now on borrowed time, burning hydrogen and helium in shells around the inert core. It ascends the asymptotic giant branch, a second expansion phase, larger and more luminous than the first. The outer layers of the star are now loosely bound, pulsating, shedding mass into space at an increasing rate. The stellar wind during this phase carries away a significant fraction of the star's total mass over timescales of millions of years. Eventually, the outer layers are expelled entirely, not explosively, but through a combination of stellar wind and pulsations, forming a shell of gas around the remaining core. This shell becomes the planetary nebula, a glowing ring or bubble of ionized gas, lit by the ultraviolet radiation from the hot core at the center. Planetary nebulae are among the most beautiful objects in the night sky. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Butterfly Nebula, the Cat's Eye Nebula. These are the shed outer layers of stars that have just finished dying, the expelled hydrogen and helium, glowing as they absorb and re-emit the radiation from the stellar remnant at the center. And the remnant at the center is a white dwarf. The carbon-oxygen core, compressed but stable, supported by electron degeneracy pressure, no longer undergoing any fusion reactions. A white dwarf is typically about the mass of the Sun, compressed into a volume roughly the size of Earth. Not as dense as a neutron star, the electrons are still present and providing the degeneracy pressure rather than having been forced into the protons as in neutron star matter, but still enormously dense by ordinary standards. A white dwarf is not generating any energy. It is not fusing anything. It is just hot, a relic of the heat generated during the star's active life, and it is slowly radiating that heat into space. It is cooling. It will cool for billions of years, dimming from white to yellow to orange to red to, eventually something too dim to observe, a black dwarf. No confirmed black dwarfs exist yet because the universe is not old enough. The cooling timescale exceeds the current age of the universe. All the white dwarfs that have ever formed are still white, or at most, a faint, dim orange. The first black dwarfs are still in the future, but white dwarfs are not always quiet. In a binary star system, a system with 2 stars orbiting each other, a white dwarf can have a companion that is still in its active life, still fusing hydrogen, still occupying space. If the 2 stars are close enough, the white dwarf's gravity can pull material from its companion, hydrogen from the companion's outer layers, streaming across the gap between them and accreting onto the white dwarf's surface. This accreted hydrogen accumulates on the white dwarf's surface, compressed and heated by the white dwarf's gravity, until it reaches the temperature for hydrogen fusion. At that point, the hydrogen on the surface undergoes a thermonuclear runaway, a sudden, explosive ignition that briefly makes the white dwarf enormously bright. This is a nova. Not a supernova, a nova. A surface explosion that blows off the accumulated hydrogen but leaves the white dwarf itself intact. The process can repeat. More hydrogen accretes, more fusion occurs, another explosion. Some novae are observed to recur on timescales of years to decades, but if the accretion continues and the white dwarf's total mass grows past the Chandrasekhar limit, 1.4 solar masses, a different event occurs. The entire white dwarf, not just the surface layer, becomes unstable. Carbon fusion ignites throughout the degenerate core in a thermonuclear runaway that cannot be contained. The white dwarf explodes entirely. This is a Type 1a supernova, a different mechanism from the core collapse supernova of massive stars, but producing a similar luminosity. Type 1. A supernovae are extraordinarily useful to astronomers because they are, to a good approximation, standard candles, events with a predictable luminosity that allows astronomers to calculate how far away they are. Type 1. A supernovae were the tool used to discover the accelerating expansion of the universe in 1998, the discovery that led to the concept of dark energy and the Nobel Prize in Physics in 2011. Even in death, stars are doing science. The elements iron is being made right now, not here, not on Earth, not in any laboratory, not in any industrial process. In the cores of massive stars currently burning silicon, iron is accumulating. It is accumulating silently, patiently, building toward the Chandrasekhar limit that will end the star, at a rate determined by the temperature and density of the silicon burning shell surrounding the inert iron core. The iron does not know it is accumulating. The star does not know what the accumulation will trigger. The physics just proceeds. Stellar nucleosynthesis, the production of chemical elements inside stars, is one of the major conceptual achievements of 20th century astrophysics. Before the 1950s, the origin of the elements was genuinely unknown. The early universe produced hydrogen and helium and small amounts of lithium, the primordial abundances, the elements present before any stars existed. Everything heavier than lithium, every carbon atom and oxygen atom and nitrogen atom and iron atom in the universe, had to come from somewhere. The answer, worked out by Fred Hoyle and William Fowler and Geoffrey and Margaret Burbidge in a landmark 1957 paper known as B2FH, is that it came from stars. The periodic table is, in a meaningful sense, a map of stellar processes. Hydrogen and helium, mostly primordial, made in the Big Bang with some additional helium contributed by stellar burning. Lithium, beryllium, boron, not made in stars. These elements are too fragile. They are destroyed rather than produced in stellar interiors. They are made primarily in cosmic ray spallation, the fragmentation of heavier nuclei by high-energy cosmic rays in the interstellar medium. Carbon, oxygen, nitrogen, made in the helium-burning cores and shells of stars, dispersed by stellar winds and supernovae. Neon, magnesium, silicon, sulfur, argon, made in the later burning stages, carbon burning, neon burning, oxygen burning, in the interiors of massive stars. Iron, cobalt, nickel, made in silicon burning, the final fusion phase before core collapse. Everything heavier than iron, not made by standard stellar fusion. These elements require neutron capture, the addition of free neutrons to nuclei, building heavier isotopes. There are two versions of this process. The slow process, the S process, occurs in the interiors of asymptotic giant branch stars. the puffy red giants that are the late evolutionary stage of low-mass stars. Free neutrons are captured by nuclei at a slow rate, allowing unstable isotopes to decay before another neutron is added. This process produces elements up to lead and bismuth, roughly half of the heavy elements. The rapid process, the R process, requires an environment with an enormous flux of free neutrons, so that neutron capture happens faster than radioactive decay. The R process can build nuclei far from the valley of stability, creating very neutron-rich isotopes that then decay back towards stability by emitting electrons. The R process produces elements heavier than iron, gold, platinum, uranium, and many others. For decades, the supernova was considered the most likely site of the R process. In 2017, that picture changed. Or rather, it was confirmed that it needed to change. On August 17, 2017, gravitational wave detectors LIGO and Virgo detected a signal from the merger of two neutron stars approximately 130 million light-years away. This event, designated GW170817, was the first gravitational wave detection from a neutron-star merger, and it was accompanied by an electromagnetic counterpart, a gamma-ray burst detected by the Fermi satellite, followed by a fading optical and infrared source that was observed by dozens of telescopes worldwide. The optical and infrared source was a kilonova, the light from material ejected by the neutron-star merger, and the spectrum of that light contained the spectroscopic signatures of R process elements, gold, strontium, heavy elements, freshly made in the neutron-rich environment of two neutron stars colliding and merging. GW170817 was direct observational confirmation that neutron star mergers are a site, possibly the dominant site, of R process nucleosynthesis. The gold in the universe is made when neutron stars collide, not when stars explode, but when their remnants, sometimes millions of years after the explosions that made them, find each other in binary systems and spiral inward under gravitational wave emission until they merge. The chain is layered. A massive star forms from a cloud of gas enriched by earlier stellar generations. It burns through its fuel sequence. It explodes as a core collapse supernova, producing a neutron star and dispersing carbon, oxygen, silicon, and iron into the interstellar medium. The neutron star, if it has a companion neutron star from a companion star that also exploded, will over millions to billions of years spiral inward under gravitational wave emission. When the two neutron stars finally merge, they produce gold and platinum and uranium and the other R process elements dispersed into the interstellar medium in the kilonova explosion. New stars form from this enriched gas. New planets form from the dust in those protostellar disks. And on one of those planets, at some point chemistry becomes biochemistry, and the elements assembled in stars and stellar remnants become the molecules of life. Your iron came from a supernova. Your gold came from a neutron star merger. Your hydrogen came from the Big Bang. You are the accumulation of a chain of stellar events stretching back almost to the beginning of the universe. This is worth sitting with for a moment, separate from any larger meaning you might want to attach to it, not the philosophical version, not the poetic assertion that we are stardust, offered as a comfort or a wonder without much grounding. The specific, chemical, traceable version. There is iron in your hemoglobin that was forged in the silicon-burning shell of a star that died more than 4 billion years ago, dispersed in a supernova, incorporated into the molecular cloud that collapsed to form the solar system, accreted into the proto-Earth, dissolved into the early ocean, incorporated into early biochemistry, and passed through an unbroken chain of biological inheritance until it ended up in you. The chain is real. The chemistry is real. The tracing is imprecise. We cannot identify the specific star, but the general picture is well established and not seriously disputed. You are, in a specific and literal sense, the descendant of a stellar death. The things we still don't know. There is a supernova happening in a galaxy somewhere in the observable universe, approximately once every second. This is an estimate. The rate of supernova per galaxy is roughly 1 to 2 per century in a Milky Way-sized galaxy, and the observable universe contains hundreds of billions of galaxies, so the numbers work out to something in the vicinity of 1 per second, integrated across all those galaxies, 1 per second. That means that in the time it took to read this paragraph, several massive stars somewhere in the universe have ended their lives in core collapse, sending shockwaves through their interiors, producing neutron stars or black holes, dispersing elements into their host galaxies. Most of these supernovae are not observed. Most of them are too far away, or obscured by dust, or happening in galaxies that no telescope is currently pointed at. The observable universe is large, and the surveys of it are incomplete. But in our own galaxy, the Milky Way, there have been only a handful of supernovae in recorded human history. The most recent confirmed Milky Way supernova visible to the naked eye occurred in 1604, observed by Johannes Kepler. Before that, the 1572 supernova observed by Tycho Brahe, the 1054 supernova that produced the Crab Nebula, a few others in the historical record. The galaxy is producing supernovae, probably 2 or 3 per century, but most of them are hidden behind the dust of the galactic disk. We are, statistically, overdue for a visible galactic supernova. Several candidates are known. Betelgeuse is the most discussed, though its recent dimming in 2019 to 2020 turned out to be caused by a massive convective plume of gas and dust, rather than any sign of imminent core collapse. Eta Carinae, a massive and unstable star about 7,500 light-years away, is another candidate. When the next galactic supernova occurs, and it will eventually, it will be the most observed astronomical event in history, with neutrino detectors and gravitational wave observatories and every telescope on Earth and in space trained on a single point in the sky. But what will those observations tell us? The honest answer is more than we know now, but probably not everything. Core collapse supernova theory has made enormous progress since the 1960s, when the basic picture of neutrino-driven explosion was first proposed. Three-dimensional simulations of the collapse and explosion have become increasingly sophisticated, incorporating general relativity, detailed neutrino physics, magnetohydrodynamics, and convection in ways that were computationally impossible even 20 years ago. These simulations have succeeded in producing explosions in virtual stellar interiors under conditions that match some observed supernovae. But the mechanism is not fully understood. The neutrino-driven mechanism is the leading explanation, but the energy transfer from neutrinos to the stalled shock is not efficient enough in simple spherically symmetric models to revive the shock. The revival requires convection, turbulent mixing in the region behind the shock, and possibly the standing accretion shock instability, a hydrodynamic instability that can develop in the post-shock region and enhance the efficiency of neutrino energy deposition. The three-dimensional structure of the explosion matters enormously. Supernovae are not spherically symmetric events, and the departures from symmetry are not incidental but may be part of what makes the explosion work. The asymmetry is real and observable. Neutron stars, the remnants of core collapse supernovae, are observed to have large velocities relative to their birth sites. Some neutron stars are moving at hundreds of kilometers per second. This is called the natal kick. The standard picture of a spherically symmetric explosion would not produce large natal kicks. The asymmetry of the explosion, the shock wave breaking out preferentially in one direction, is what kicks the neutron star in the opposite direction. We can measure the natal kick in individual pulses. We cannot yet fully explain the mechanism that produces it. The three-dimensional simulations are consistent with the existence of natal kicks, but the relationship between the explosion asymmetry and the kick velocity is not precisely pinned down. There is also the question of what happens inside the neutron star itself. The equation of state of matter at nuclear density, the description of how this matter behaves under the conditions present in a neutron star interior, is one of the outstanding problems in nuclear astrophysics. Different equations of state predict different maximum neutron star masses, different neutron star radii, different properties of the dense matter at the core. Gravitational wave observations from neutron star mergers like GW 170817 provide constraints on the equation of state. Because the gravitational wave signal carries information about the tidal deformability of the neutron stars, how much they deform each other's shapes as they spiral together. This puts limits on the neutron star radius and, indirectly, on the equation of state. NICER, the Neutron Star Interior Composition Explorer, an X-ray telescope mounted on the International Space Station, is measuring the sizes and masses of neutron stars by observing X-ray emission from hotspots on their surfaces. Combining mass and radius measurements gives direct constraints on the equation of state. The answer is not fully in yet. The picture is becoming clearer. But what is in the core of a neutron star, whether it is purely neutron matter or quark matter, or some strange exotic state, is still open. And then there are the things we do not know that we do not know, the open questions that nobody has yet thought to formulate. Supernova 1987A is the most studied supernova in history, the one that produced the neutrino detections mentioned earlier. Its remnant is still evolving, observable across the electromagnetic spectrum, and has been watched continuously since the explosion. At the center of the remnant there should be a neutron star, the product of the core collapse. 37 years after the explosion, astronomers have recently found evidence that this central compact object exists, detected in X-ray emission and radio emission from the warm dust that surrounds it. But the neutron star itself has been harder to pin down than expected. Its direct emission is still faint enough to be embedded in the much brighter emission of the surrounding nebula. This is not a crisis. The timescales involved are short by astronomical standards, and the remnant is still evolving rapidly. But it is a reminder that even the nearest, best-studied supernova remnant in modern astronomy still holds questions that have not been answered. The universe is generous with its violence. It is less generous with its explanations. Tonight, something is happening right now, not hypothetically, not in general. Right now, at this moment, in a galaxy the light from which left before the Earth had finished forming, a star is completing its silicon-burning phase. The iron core is approaching the Chandrasekhar limit. The electrons are losing their ability to hold it up. The collapse is minutes away, or hours, or possibly already underway. The neutrino burst already propagating outward, the shock wave already bouncing, the explosion already beginning, and the light from it will not reach Earth for millions of years. You cannot know this is happening. Nobody can. The distance is too large, the light is too slow, and there are no instruments that can detect a stellar collapse across intergalactic distances except in the neutrinos, which pass through everything and are detected only by accident. The event is real. The event is occurring. The event is invisible. This is the thing about stellar deaths that takes the longest to absorb. They are not rare. They are not dramatic from the perspective of the universe. They happen at a rate of approximately 1 per second, distributed across hundreds of billions of galaxies, and they have been happening since the first massive stars formed a few 100 million years after the Big Bang and ran through their brief lives and exploded. The universe has been filled with stellar deaths for almost as long as it has existed. Each death disperses elements. Each death enriches the interstellar medium. Each death contributes to the inventory of atoms available for future star formation, future planet formation, future chemistry. The deaths are not incidental to the story of the universe. They are part of the mechanism by which the universe produces complexity. Betelgeuse is there tonight. If you're in the northern hemisphere and the sky is clear, it is visible as the bright reddish star in the upper left of the Orion constellation. It is not going to explode tonight, with high confidence. The estimates of its remaining lifetime range from tens of thousands to hundreds of thousands of years. But it is a red supergiant in the late stages of its life, burning helium and possibly more advanced fuels in shells around a contracting core, shedding mass into space at a rate of perhaps a solar mass every 10,000 years or so, surrounded by shells and asymmetric structures that record its recent mass loss history. When Betelgeuse does explode, whenever that is, it will be visible from Earth in daylight for weeks. It will cast shadows at night. It will be the brightest object in the sky other than the sun and the moon. It's about 700 light-years away, close enough to be spectacularly visible, but far enough to be safe. The lethal effects of a supernova, if any, are confined to within a few tens of light-years of the explosion. The explosion will be observed by whatever astronomical infrastructure exists at the time. If humans are still here, and still watching the sky, it will be the most thoroughly documented supernova in history. Every instrument, every frequency, every second of the light curve. The neutrinos will arrive hours before the visible light, and the neutrino detectors, whatever they are by then, will give astronomers hours of warning. The calcium in your bones was made in a star. The iron in your blood was made in a star. The oxygen you're breathing was made in a star. The carbon that forms the backbone of every organic molecule in your body was made in a star. Not the same star, different stars. Stars that lived and died before the solar system existed, that dispersed their contents into the molecular cloud that would eventually collapse to form the sun and its planets, that contributed their elemental inventories to the rock and water and atmosphere that eventually became the context in which life appeared. The chain from stellar death to living organism is long and indirect, and depends on a sequence of events that could have gone differently at many points. But the chain is real, the chemistry is real, the iron is real, stars die, They have always been dying. They will die for a very long time still, for trillions of years, until the last low-mass red dwarfs exhaust their hydrogen and cool to darkness, and the galaxy goes quiet. The universe in its old age will be a collection of stellar remnants, white dwarfs, neutron stars, black holes, and cold dark objects too dim to observe. The epoch of star formation is not over, but it has passed its peak. Most of the star formation in the history of the universe occurred between 2 and 6 billion years after the Big Bang. We are now at 13 billion years, and the rate is lower, declining, and will continue to decline. The stars are not permanent. The sky that looks eternal, that has looked the same to human eyes for all of recorded history, is changing, slowly on timescales that make human history look like an instant, but changing. Stars forming, burning, dying, dispersing. The night sky you see tonight is a snapshot of a process that has been running for 13 billion years and will run for trillions more. And the snapshot is extraordinarily detailed and extraordinarily beautiful, and also, in a specific sense, temporary. Every star you can see tonight will die. The sun will die. Betelgeuse will die soon, by stellar standards. The faint red dwarfs, Proxima Centauri, the closest star to the sun, will burn for trillions of years, but will also eventually exhaust their fuel and cool to darkness. The sky is full of things that are dying, some slowly, in the particular quiet way that low-mass stars die, expanding and shedding their outer layers, and leaving behind a white dwarf that will cool for the rest of the age of the universe. Some violently, in the fraction of a second that core collapse requires, in the brief incandescent aftermath of an explosion that temporarily outshines a galaxy. None of this is tragedy. It is the mechanism by which the universe processes matter, concentrating it into dense hot objects where nuclear reactions can occur, then dispersing it back into the interstellar medium where it becomes available for the next cycle of concentration. Stars are not endpoints, they are events in a long ongoing process of matter cycling through the universe. You are part of that cycle. The atoms in you were part of stars before they were part of you. They will be part of other things after they are part of you. The cycle does not have an endpoint visible from here. The night is quiet. The building is doing whatever buildings do at this hour. The sky is out there, or the ceiling is out there, or whatever is between you and the stars is out there, doing its usual thing of being present and unremarkable, and somewhere in the sky, a star is at the limit. The iron core is heavy. The electrons are losing the argument. The collapse is very close now in that star, wherever it is, in whatever galaxy, at whatever distance. The surface does not know. The light leaving the surface right now carries no information about what is happening in the core. The surface is calm. The surface is just glowing, the way stars glow, the way they have always glowed. And then the core goes, and the electron degeneracy pressure gives way, and the collapse begins. And in a quarter of a second, something that was Earth-sized is city-sized, and made almost entirely of neutrons, and spinning at a significant fraction of the speed of light, and surrounded by a shock wave moving outward through the star at a quarter of the speed of light and carrying enough energy to outshine a galaxy. And the neutrinos are already out, passing through the star's matter almost without interaction, spreading into the galaxy at the speed of light, and some of them will arrive at Earth and pass through every detector, and every person, and every mountain, and the entire planet without leaving a trace. And hours later, The shockwave reaches the surface of the star, and the star brightens enormously for weeks, and the elements are out, scattered into space, on their way to becoming something else. This is what happens when a star dies. It does not end. It becomes